Hello and welcome to another video. In this video we're going to be working on number of dice rolls with target sum. And in the problem you have n dice and each dice has k faces numbered 1 through k. Given 3 integers nk and target, return the number of possible ways to roll the dice so that the sum of the face of numbers equals the target. And so let's go through the example. So in the first example you only have 1 die and it's a 6-sided die and you're trying to get 3, so the only way to do that is get a 3. In the second one, you have 2 die and it's a 6-sided die, and you're trying to get a 7, so there's 6 ways to do that, and they show you the ways here. And in the third one, obviously, you can't see this, but essentially it's just some big number. So when you're asked for these problems that ask you to calculate the total number of some things happening, it's almost always going to be either a DP problem or a backtracking problem, right? For things like counting, counting ways or all these things where you're on a stair, you can go some stairs at every iteration, and how many ways can you get to the top? All these things are DP. And then backtracking are more you have some set of things to pick from, and you're asked what are all the different ways I can arrange these items, right? So you have something like A, B, C, D, E, and you're asked okay, what are all the different ways I can arrange these items? So maybe something like B, A, C, D, E, and so on and so on. And so the first thing you want to look for is, can I do this in DP? And if you can't, then probably going to have to do it backtracking. And also the constraints tell you a lot about it. So typically if you have to use both constraints for backtracking because it's super inefficient, these things will be really small. They'll be 10, 20, 30, something like that. So in this one, it's going to be a pretty clear DP problem with some pretty obvious states, I'd like to think. So definitely, if you weren't able to solve this one, you should do more DP problems, because once you do enough DP problems, it should be pretty clear what the states are and kind of what it's all looking like. Okay. So for DP problems, we need a couple things, right? As always, we need states, for what are the things we store in our function, a base case or base cases, and a recursive cases. So for the states, we want to store the minimum amount of information that we can to actually get something here, right? Sometimes you might be able to store some things, but then you realize you don't really need both, or you can turn something into something smaller. That helps a lot, right? You want to basically minimize your time and space, and the bigger the state, the worse the time and space is going to be, assuming every state is possible, because at the bare minimum, your time will be all your states multiplied by each other. So here, you basically have n die, and each die has some number of faces. So you obviously don't need k, because k will be the same for every single die, right? So you don't need to know how many faces each die has, because they're all the same. But you do need to know how many die you've rolled, and there's not really anything you can do to prevent that, right? Because if you are calculating how many ways you can get a target, you need to know how many die you've rolled. You can't really do anything to save that. So one of the states is going to be number of die you've rolled, right, or dice or something. Okay, and so number of dice you've rolled. And the other thing you need to know is what's your total score. That's the other thing. You can't really prevent that, right? You need to know how many dice you've rolled and what's your total score to see if you've actually gotten the target. And it's a total score. And the way we're going to do this is, instead of total score, I'm going to have total score left. It's going to make it a lot easier. Well, not a lot easier, but one way to do it. Essentially, if the total score left is going to start off at the target, and then every time we roll a die, we'll just subtract by what we rolled. So for example, if our score here is 500, and our dice have 30 sides, and we roll one of them and we get a 30, let's say, then we have 470 left to go, and then our goal is basically to get to 0. So these are going to be the two things. Now there's going to be a few base cases, so I definitely want to think of those. So one of them is total is, or actually not total is. So first obvious base case is we've rolled all our die, right? We have rolled all die. And so when we've rolled all of our die, what do we want to do? Right? We've rolled all of them, or dice. I don't know why I keep saying die. We've rolled all our dice. What do we want to do? Well, we want to actually check what the total is, right? Or total left is. So A, if the total left is 0, then this is basically like the success, right? We've rolled all of our dice and the total is 0. That means we've hit our target. And so when you're counting combinations, you always want to return 1 here as like a success. So you roll your dice, everything is done, you've hit your goal, right? You have to roll all your dice. You can't, like, if you have 2 dice, you can't just like roll one of them. You have to roll all of them. So once you roll all of them, check, is your total the target? If it is, return 1. Otherwise, we have a couple more. So, and this is if we rolled all our dice, right? Rolled. Oh, actually, I already wrote this up here. So the other way, if we rolled all of our dice and the total isn't 0, so otherwise, return 0. Because basically, if we've rolled all of our dice and we have a total remaining, that means we didn't reach our target. So that's like a failure. And this is really common in these DP states. So in these DP like count problems, you want to return 1 success, 2 failure. These are the things you want to be returning. Or not 2, it's going to be 0. So 0 for failure and 1 for success. That way you can easily count them up because you can just say like, okay, let me add all of my DP cases. Every time there was a success, there's going to be a 1, so I can easily get like a total. Okay, so that's one of the base cases, right? We've rolled all of our die. Now you can just leave it here. This would totally work. But there's another one that you can end early at, and that's going to be we have a negative total, right? And that's one we're going to check for. So we have a negative total, return 0. So let's say we have like, I don't know, a billion die or whatever. We have some die, and our total is negative. Like our total is -3, and we still have to roll some die. We obviously can't get, or roll some dice. We obviously can't get a 0 for our target, right? Like if we start at remember we're going to start at the target we're trying to go for. So if we start at like 500 and we roll and roll and roll, and then we get to like -5, but we still have like 5 dice left. Anytime we get to a negative number, our number is only going to decrease, right? Because we're essentially trying to get to 0. So anytime you have a negative total, you just want to return 0 right away. You don't need to like keep recursing because you're never going to get to an answer. So that can be that's one way to like end the problem early. Now you could still totally, I think it'll still totally work if you don't do this. Like if you just always roll till you have no dice left, that's fine too. But this is just going to be like an easier way to make it a little bit faster. Okay, and now the recursive case is kind of obvious. So recursive case is basically for the die we are on, loop from 1 to k, right? So essentially if we have like a 6-sided die, we're basically simulating, rolling a 1, 2, 3, 4, 5, 6, and recurse appropriately. So what I mean by that is like, let's say we are on some die, like let's say we're on die number 3, and the total we have left is 50, and our k is like 6. So we would say like, okay, let's simulate rolling a 1. What would rolling a 1 look like? Well, we'll be on the next die, so it'll be dp of 4, and then it's going to be the total minus whatever we rolled. So if we rolled a 1, it'll be dp 449, then the next one will be like dp 448, and so on, right? We're basically just decrementing from the total whatever number we simulated we rolled. So we're just going to have a loop, looping 1 through whatever our biggest number, whatever our k is. Because for every die, we can roll 1 through k. And that's pretty much it. Obviously, we also have a cache, but that's pretty much it. So it's just a basic DP problem where our states are going to be our number of dice we have rolled, and then what our total is so far. And then in every single problem, we just simulate a roll from 1 to k. And this is another thing you want to get used to figuring out, like, will this pass right away? So if you think about it, how big will our stuff be here? So we have 2 states. We have a target and an n. N is only 30. So basically, the number of states we have is 30 and 1,000. And then in each actual function, we'll do something 30 times. So this will be like 900 and 1,000, which is roughly 1,000 and 1,000, which is 10 to the 6th, which will pass. So, yeah, I think anything under like 10 to the 8th or something passes. And obviously backtracking would fail here. I don't even know how, you could do backtracking, but backtracking is usually like a 2 to the n function. So obviously like 2 to the 1,000 or something wouldn't work. And yeah, and I will also, so we can code it up and then we'll talk about some optimizations you can make as well. So we're going to have a cache for the DP as always. And I'm just going to code up the memoization solution. I definitely think, especially if you're new to DP, just practice doing memorization. That's like 95% of what you need to know. The other stuff is like kind of just like almost syntactic sugar type of stuff. Like it almost never really helps with performance, or very rarely. And the amount of effort you have to do is like a lot more. So, okay, so we're gonna have a def dp, and we're gonna have essentially our dice rolled, and we'll have a total. And so if dice equals n, that means we've rolled all of our dice, so we need to check, is our total 0? So you can actually do this kind of in a clever way. You can just return total equals 0. Basically what this will do is, if the total is 0, it will return true. If it's false, it'll return false. And you can add trues and falses in Python. So you can just add if you add a false and true to a number, false will be 0 and true will be 1. So this will essentially be the same as a 1. Now, this is the same thing as just coding it like this, right? So you could say like the total equals 0, return 1, else return 0. Obviously, in other languages, you're not going to be able to do this because you can't like add booleans to int or something, but in Python you can. So. Okay. So now the other case we have is if our total is negative. So if total is negative, we can just return 0 right away because there's no way to get to a 0 total because we're only decrementing. Now we check for the case where our stuff is in the cache. So if dice total in cache, return that. Okay, and I think that should be all of the base cases. So now we just do the recursive case. So essentially, we'll just set our result to 0, and we will loop. Oh, we also need that mod because our value can get too big. 10 7. So we need to loop for every single possible roll we can. So we'll just say like for I in range. And if it's like a 6-sided die, we can get anywhere from 1 to 6. So we'll loop from 1 to k plus 1. And now we'll just add these numbers. So we will say result equals result plus dp of whatever we rolled. So it's going to be dice is going to go up by 1 because we just rolled a die, and total is going to decrease by whatever we rolled. So total minus I, and then we will mod it by mod to keep these numbers small. Yeah. And we do that, then we store it in the cache. So we'll say cache dice total result and return result. And here we can just return dp of 0, 0 because essentially in the beginning we have no dice rolled, and actually our total shouldn't be 0. Remember, we're decrementing to 0, so our total should start off as target. It should decrement to 0. You can, like I said, you can do it the other way where you can start at 0 and you can say when your total equals target, return true, and when your total is greater than target, return false. Like that works too. Okay. And there we go, and it's reasonable. So yeah, so let's talk about the time and space, and then let's talk about some optimizations. So for the time here, basically the way you calculate time for DP is you multiply your states if every state is possible, which in this case it obviously is, right? Yeah, definitely. I think you can get like if you can hit the total, you can obviously hit like any number below the total because you can just like roll 1 or 2 less or whatever you need for your die. So this is going to be the dice is going to be O of n, the total is going to be O of target. And in the loop, we're looping 1 to k, so it's going to be like this. For the space, in DP, it's typically the size of your cache, and then if there's anything bigger than that, you store that as well. So the size of our cache is just all of the states, which is just n times target. And then the most we can ever recurse is n times, because we would just recurse, like, every single recursive stack frame would just be like another die. So that's going to be less than the cache. So the upper bound of the space is just the size of the cache. Okay, and then for some optimizations, so if you do want to, like, you know, if you aren't new to DP, if you do want to, like, optimize this a little bit for space performance, you can do a few things. And I'll include this, once again, the space optimized bottom-up video. But essentially what you can do is you can look at what your states are changing to, right? So in your DP, you are basically incrementing dice by 1 every single time. So this can be optimized. You can get rid of this dimension if you wanted to. So then you would just have O of total for the O of target for the space, because every single die just relies on the die before it. So that's one thing you could do. Another thing you can do is actually, for this total can only go down by 30. every single time, right? Because k is like 30 here. So if your total can only go down by 30, you only need to store like an array of 30 totals. So that's the other way you could optimize it. Instead of getting rid of this dice dimension, you can actually cut down this total dimension to only be O of k, basically. So then your space, if you do optimize it, would be O of this, which would be significant because target's like 1,000 and k is like 30, right? So you could do that as well. It's going to be a little bit trickier because, like I said, you have to hold 30 states, but it's kind of straightforward. You basically just hold an array of 30 totals, and then for every new die, you just get 30 new totals and discard your old totals and things like that. So yeah, and I'll include the space optimized video if you want to do that. But those are the things you can look for and you can do if you want to do some more advanced DP. But yeah, that's going to be all for this one. So if you did like this video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.